So will be discussed soon. The question number 4 is about DRAM, which I also haven't started. I will start on DRAM right after this. Okay, so again, this will be covered soon. Last question is a simple question. I showed this chart, and this refer to GDC. Okay, GDC is the same as the GDS. GDS is essentially the slope, the conductive slope of the IDVD curves. Okay. We go back to question number 1. Ask about high injection effect, and so for BJT, high injection means that the electron injected from emitter into the base exceeds the base doping. Okay, base doping is Na. So when the before high injection, the charge neutrality in the base is between the hole, positive charge of the holes, and the fixed acceptor atoms. Okay, but when the electron, in that case, the electron density is negligible compared with those two. But when electron density is very high, much higher than the doping density, like in this region here, then the whole density has to go up in order to maintain charge neutrality. So in that case, if you apply P equal to N into this expression, the PN product, if they are about the same, then both P and N go proportional to e to the QV over 2kT. Okay, that's why you see the change of slope. I also addressed this in chapter 3, shown here. The for PN junction, okay, you can see the charge neutrality is means that the injected minority electron in the base should be the same as the injected hole density into the base, the majority. And when the delta NP is much smaller than Na, and then delta PP is also much smaller than Na, then we have this e to the QV over KT relationship from the basic equation. But if the delta NP, let's see, also delta PP, they're the same, is much higher than PP, which is Na, then each of them goes as the square root of the right side, which is Na to the U QV over 2kT. Okay. So the charge neutrality in the base under high injection is achieved by the whole injection, the above and beyond the doping, the base doping Na. Second question is about AT SRAM, which we have not discussed. AT is not a basic mainstream SRAM structure. Okay, 6T, we discussed the 6T, which is basically 2 CMOS inverters plus 2 N transistor, and those have the, of course, density is high because of 6T compared with others here, but AT has even lower density because you have even more transistor than 6T. But the additional benefit is not much compared with 6T. Okay. So usually when people go to 60, we achieve those the cell stability compared with the others, and there's no need to go to 80. It's only for special applications they go to 80. Actually, it's not just 60 and 80. If you look it through the publications, there's 70, and then there's even 90. Okay, so 80 is not unique in that sense. Okay, you can, but minimum is 60 to achieve those the stability and the low current, no power condition. And once you achieve that, you can add more transistor to get more like stability or signal to noise ratio and all that stuff. But at the expense of density, people usually don't go for that. All right, so that's the questions. We go back to chapter 12. Yeah. So last class we finished the static RAM. Okay. Now we talk about dynamic RAM. Dynamic RAM is a very small cell, one transistor and one capacitor. And there was a question about the capacitor. Actually, there's a configuration where the capacitor is stacked over the transistor to minimize the area of the cell, and that's what is being practiced. Before that, in early days, it's planar, too much area once you scale the DRAM smaller and smaller. And then there's also deep trench for a couple of generations. But now all the DRAM are stacked in order to minimize the cell size. All right, so it's very simple. There's the word line goes connect to the gate of that transistor, and the bit line is the either source or drain. Let's say it's drain. The source is either is a capacitor. So this capacitor can be, if there's a charge, if there's no charge, then the side is grounded. If there's a charge, then this is high voltage like VDD. Okay, and so let's see how this DRAM cell works. Okay, so this is also when you have a so you gotta look at this read and write back. And the reason is that when you read a DRAM cell, it's different from SRAM. Okay, SRAM read is non-destructive. Okay, so you read SRAM, and then you after that the memory bit stays the same as before. But for DRAM, when you read, the signal is essentially destroyed. So you have to write back. Okay, for example, in this case, the word line, if the word line opens, okay, the V node, if there's a charge, if there's no charge, of course, the bit line is ground. Okay, it's no problem. But if it's charged, then this charge will spread out. But there are many other cells. So once you spread the charge, the charge is no longer, the capacitor is no longer fully charged. So this readout is destructive. Okay, so you must have a mechanism to write back. Okay. In fact, even if you don't read, if this V node is if this junction is reverse biased, and so you have a positive charge, over time the leakage current will eventually discharge the capacitor to ground over a long time. So that's why it's called dynamic. So even if you don't need the information, you still to read it out. And if it's stored 1, then you write it back. Okay, so this shows how it works. Well, first of all, in this case, there's only 1 bit line through the cell. So you need another bit line complementary, this bit line true, bit line complementary to get a differential signal. So this bit line is through a cell, is a dummy cell that's not opened by this word line voltage. Okay. I will show that. We'll show that later. But the waveform for the signal for the read and write back cycle is shown here. So the word line, first of all, the word line goes from 0 to VDD to turn on the gate. Okay. Actually, it goes over VDD. We'll discuss that later. This is called the boosted word line. And so let's assume that 0 means that the node is there's no charge on the capacitor in the beginning. So V node is ground. Okay. So you can see when it's 0, V node is ground. Okay. And both bit lines are pre-charged to VDD over 2. This is different from SRAM. In the SRAM case, the bit lines are pre-charged to VDD. In this case, both bit lines are pre-charged to VDD over 2. Exactly half between the 0 and the VDD. And then once the gate is, once this transistor is turned on, then the side with the connect to the cell, the BLT will drop because this was VDD over 2, and this is ground. Right? This is really 0. So this will drop a little bit. So you can see the BLT will go down a little bit. BLC, it's not connected to anything, so the BLC stays the same. Okay? But BLT goes down. So with this, we can sense that this is 0 there. Okay? Now, if it's 1, if it's 1 means that V node is VDD before it's open. So if we open, then BLT will go up from VDD over 2. This side is VDD, so we'll go up. Let's see, BLT will go up above VDD over 2. Okay? So we can sense that if BLC is higher than BLT, then it's 0. If BLT is higher than BLC, then it's 1. That's stored here. Okay. So this is the read part. Now for the write back depend on the sense amplifier here. Okay. This sense amplifier actually is it's exactly a SRAM cell. It's 2 inverters connected back to back. Okay. Now, but the power supply, the VSP and VSN, in the beginning, they are not connected to VDD and ground. Okay, for SRAM, the PFET is VDD and that's ground, but in the beginning here it is VDD over 2. Okay, so this has no effect during the read, but the write back, during the write back, we apply VDD to VSP and ground to VSN. Okay, so now it becomes a CMOS SRAM, 2 inverter back to back. Now we know that in this case, it's got 2 stable states. Let's see. Let's go back to that situation here. Yeah. So it looks like this. There are 2 CMOS inverter back to back, and the upper the power supply is connected to VDD and 0. So that means there are two stable states, either A or B. Either left side is high, right side is 0, or left side is 0 and right side is VDD. Okay, now which, let's go back here. Okay, so which state does it go to? Well, it depends on whether left side is higher than the right side, or whether left side is lower than the right side. Okay, in the read 0 case, the left side is lower than the right side. The right side is VDD over 2. The left side is a little bit lower. So in that case, this sense amp, after you apply VDD and 0 to the power supply, will go to the state where the left side is 0 and right side is VDD, which means that, okay, you can see here that the bit line, if it's really 0, then the BLT becomes 0 and BLC becomes VDD. Okay, but if it was a 1, if you read 1, then BLT is a little higher, left side is a little higher. Then the high side go to VDD, and the low side go to 0. Okay, so once this happens, BLT goes to VDD, BLC goes 0, and that write back the full VDD back to the node. Okay, and so this is so with this kind of sense amp, it accomplishes the write back operation to when the information, the bit was destroyed due to readout, but you write back with the full 0 of VDD by this the sense amplifier action. Yeah. The last point is that the word line usually goes to VDD plus VT higher. Now that's because if the write back is ground, that's no problem. Okay? But if the left side is VDD, okay, let's say in this case, okay, in this case, if this is VDD and you want the V node to be VDD, but if the word line only go to VDD, it will not make that happen because this can only go to VDD minus VT, because then the right side, the node is the source. Okay, so VGS is the word line voltage minus V node, and if that's VDD, then the V node can only go to VDD minus VT, because above that this transistor turns off. It's in subthreshold. So in order to make the V node go all the way to VDD, just like left side, the word line, the gate voltage has to go a little higher, VT higher than VDD. In that case, the V node is well, the transistor is on until the V node becomes VDD. Okay? So that's so-called booster word line technique. Okay. I mentioned about the complementary bit line. So this shows the cell. For example, we consider okay. So we consider this cell. This is word line N. The word lines N, and then the bit line N. Bit line complementary is this line, which is connected to a cell that's not turned on by the same word line. This word line turns on all the cell on this line, but not here. Okay, so so this is a bit this B line complementary is through a dummy cell, and but to make this happen, we have to use the so-called folded B line architecture, so that the area of the cell actually is 8 square f square. F is the minimum feature size. Okay, usually it's 4f square if you have a cell at each cross section between B line and Y line. But now you sacrifice area by a factor of 2. So that's the trade-off between the cell density and also the B-line architecture. Okay. This is good because then we have the differential readout with the B-line and B-line complementary, the differential amplifier. Okay, so last chart on dynamic RAM is that the transfer device, VT, the minimum VT is 0.7 volt because you want the charge, if there's a charge stored on the capacitor, you want that charge to be there for a long time before you refresh. Okay, so regardless of the power supply voltage, the threshold voltage has to be something like 0.7 volt. And so in that case, the supply voltage cannot go down below something like quarter of a volt or so. If the supply voltage cannot be scaled below quarter of a volt, then oxide thickness cannot be scaled down. So that's so DRAM cell, DRAM voltage and the channel length, of course, cannot be scaled. Okay? And that's an issue with dynamic RAM. Also, the storage capacitor is not easy to scale down either because we have to maintain a certain like a 20 femtofarad per cell or so for stability reason. And so today we have to get more and more sophisticated in the stacked capacitor technology using the back end of the line. Okay. So that's dynamic RAM. And our next topic on memory is non-volatile. Okay, or we call these EEPROM, E2PROM. And so we talk about how do they function. Okay. So here first some of the terminology. ROM usually means read-only memory, and PROM is programmable read-only memory. And if you make an EEPROM, that means erasable programmable read-only memory. And the latest is E2PROM. E2 means electrically erasable. Okay, EEPROM is can be erased by exposure to UV light, for example. We'll talk about that later. But it's not as flexible as the E2PROM because then you have to take it out of the package, okay? And that's not practical. So you have to in the package you have to using the E2PROM. Yeah, so we focus on it. This is also called a flash. Okay. Basically, the way it works is to have a charge stored in the gate insulator. Okay? And let's see. Let me just show you a quick chart here. From chapter 4, okay. Remember, we showed this flat band voltage. Okay, there's work function difference, and there's also a QOX term. That term we say is 0, because if for logic device, okay, you don't want any oxide, any charge in the oxide. But in the flash case, in this case, we intentionally put a charge in the gate insulator in order to control the flat band or the threshold voltage. Okay. So you can see that due to the oxide charge, the charge in the oxide, the shift in the gate voltage, okay, is this term, which we have before. Shift the Q minus QOX over COX. There's a minus sign. Okay, so which means that usually the oxide charge actually is negative. So negative charge will shift the gate voltage positive, okay, with the negative sign. Okay. But shown here, this is actually positive. If there's a positive oxide charge, then the CV curve will shift negatively. Okay. And the shift depends on where the charge is. Okay. It's as an integration of the charge density over the oxide thickness, but multiplied by x. Okay, so we can explain that in the next chart. Okay, so that we consider there's a small delta Q charge at a fixed thickness in oxide here, okay, indicated by this dashed line. Then we can analyze the gate voltage when you can derive this expression here. Okay, without delta Q, we have the gate equation. Okay, Vg minus work function difference, that's flat band voltage, equal to surface potential, and then this is charge in silicon. But now we have an additional term due to delta Q. Okay, and we can derive that simply by considering that if you have a delta Q here, then from Gauss law, the field will change from E1 to E2 at this point. Okay, and the change is given by the charge, the delta Q, at this position. Okay, and so we apply Gauss law here, and also Gauss law in at the gate. Okay, at the gate. So the gate charge and is given by E2, and then silicon surface given by E1. Okay, of course, charge is neutral. Now it's the gate voltage plus silicon voltage, silicon gate charge plus silicon charge plus delta Q is 0. Okay, so based on that, we can derive this expression here, which means that to get the total effect of delta Q, we integrate over the oxide thickness. It's shown here. We integrate over x, and at the end we express that as if all the oxide charge is at the interface. Okay, so this becomes over COX, and okay, so that's how the QOX is defined. Okay, QOX is defined by this integration, and Okay, so we go back to this. The charge in oxide divided by Cox. This is the equivalent oxide at the silicon oxide interface. Okay. And so this shows that for a this is a on the left side is the cell, is the non-volatile memory cell. It has something in the oxide, in the gate oxide, either a silicon nitride or a floating gate. Silicon nitride is because silicon nitride has a lot of charge traps. So the charge can be trapped by this layer here. Or we use a floating gate for the charge to get the charge to stay there. Okay, and then there's no contact to the floating gate. And the current versus V gate voltage, okay, has two cases. Okay, with no charge, let's say the VT is here. With charge, usually the charge is negative. If there's a negative charge, then VT becomes higher. VT goes positive. Okay. So no charge is this blue curve, it's a solid curve. And with charge, with negative charge, it's a dashed curve. VT is higher. So we can distinguish between 0 and 1. Okay, let's say no charge is 0, with charge is 1, by bias the gate voltage in between. Okay, so if there's a current through, that means the VT is lower, then there's no charge. If there's no current, that means VT is higher, and that means there is a charge. Okay. And okay, so next, how do we get the charge? How do we get the charge into the floating gate or the gate insulator? And so that's so-called charge injection. There are a few different ways to do it. Okay, first we consider this is called channel Hardy electron. Channel Hardy electron shown here. This is NFET. This is NFET. So if you bias the drain very high, then you have a very high field region near the drain. And some of the electrons can have energy large enough to overcome the barrier between SL2 and between the silicon and SL2, and therefore it goes into the gate. Okay, and so we can see that for this device, the BDS is fixed at 6 volt, oxide 7 nanometer. So this is very high voltage for that oxide thickness, and the MOSFET current is given by the blue curve, but there's also gate current. The gate current is due to the Hardy electron that injected into the gate in high field region near the drain. But notice that the efficiency is very low. The drain current is on the order of 10 to the minus 2, but gate current is only about 10 to the minus 10. So the ratio is 10 to the 8. So this injection efficiency is very poor. Right? And so we try to explain why that's the case here. Because for go back here. So for the electron to be injected from the channel into the gate, first the electron has to attain a very high energy. Okay. Next, so that's in the source drain direction. Next, the field in the vertical direction should be favorable for electron to go from the channel into the gate. Yeah. So those are the two conditions: a large field near the drain, and also oxide field favorable for electron injection. Now, if you apply a very high VDS, well, okay, this is for a fixed VDS, okay, but changing is a function of gate voltage. So we need the VDS to be high so that you have a large lateral field for the electron to attain a high energy. But once you do that, the oxide field is no longer favorable for electron to go from the channel into the gate. Okay, this is explained. This can be explained by next few charts. So this shows this is a the field, the two-dimensional field count. This is for double gate, but it works the same way. We cover this in the when we talk about the non-GCA model. Let's look at here. So when this is the pinch off. So once you exceed pinch off, the oxide field actually changes sign. You can see that now the field, the vertical field. So when the lateral field is high, the lateral field is such that it prevents the electron from going into from a channel into the gate. Okay. Again, we show this chart in the non-GCA model. Okay. So once the point B is the pinch off point. Okay, once you exceed this point, then oxide field is reversed. So electron, instead of going to the gate, will stay in the channel. Okay. So this explains why the efficiency is so poor. Okay. For a fixed VDS as a function of gate voltage. Okay. So we covered this in in chapter 6, the long GCA model. You can see that the field at the drain goes up beyond the saturation voltage. Okay, but in that case, the vertical field is reversed to so the electron is not to accept the electron into the gate. Okay. So instead of gate current, we can measure the substrate current. You can see from here that the substrate current actually is very high. Okay, it's about 10 to the minus 3 compared with the channel current. Okay. This substrate current is due to avalanche impact ionization due to hot electrons generate electron hole pair, okay? And the hole goes into the substrate. So this is the substrate current. This is one way to measure the amount of the hot electrons. Okay, because once you have a hot electron, you will you will produce holes, and the holes got injected into the substrate, produce substrate current. And I explained that before. Now, so instead of MFET, if you use PFET, then you have a much better efficiency. You can see that previously we used MFET, and the efficiency is about 10 to the minus 8. This you can be 10 to the minus 4, but we use a PFET. So same VDS, same oxide, same channel, but PFET. So the gate current, you can see that it peaks right here without very high drain voltage. Okay. And so in this case, we have we produce hot holes near the drain. and holes will generate electron and hole pairs. In this case, the electron will be attracted toward the gate, because for a PFAT, the vertical field is reversed. For electrons, vertical field does not encourage the electron to go into the gate. For PFAT, the vertical field is such that you will encourage the electron going into the gate. So once you have enough holes to generate electrons here, it produces a large gate current. So now the efficiency is 10 to the minus 4, much higher than the NFET case. Another way to achieve charge injection is by, we call it Forno-Nordheim tunneling. This we talked about in chapter 4. There are two kinds of tunneling. This is direct tunneling, thin oxide. But for thick oxide, and the tunneling can occur if you have a high voltage biased in the channel. So it's called Forno-Nordheim tunneling. And but the voltage has to be higher than 3 volts, because the barrier height from silicon to oxide is 3.1 eV. Okay, so this tunnel, the Forno-Nordheim tunneling current is a very strong function of the oxide field. And so in fact, it's a fairly universal function of the oxide field. As you can see, the current density. Okay? It's very steep. Okay? So to achieve, to achieve something like, let's see, 9 megavolts. So we achieve something like a milliamp per centimeter square. Okay? For a 10 nanometer oxide, we apply 9 volts. We'll achieve 9 megavolt, and then the current. Okay, so from here we can see the current is about 2 milliamp per centimeter square, and so it takes milliseconds to program a release. So even with this high voltage, okay, it still take a long time, a millisecond compared with the nanosecond switching speed. So it takes very long time. That's why the flash or the non-volatile RAM cannot be used in computation, because it takes too much to change the memory to program or erase a memory bit. Compared with the channel hard carrier we just talk about, this is much slower. This something like 1,000 times slower. Okay, but this can always be used. Okay? So in most cases, we use for a non-volatile. Let's see, for a non-volatile RAM cell. Okay, we want oxide thickness to be on the order of 10 nanometer, so that we can use the Forno-Nordheim tunneling for program and erase. If you oxide is thinner than 10, then we have direct tunneling. Once you have direct tunneling, even if you get a charge into the floating gate, but it can come out. Okay? So for a non-volatile memory, you don't want oxide to be too thin. It cannot be too thick. If it's too thick, then you need a large voltage to achieve this 9 megavolt per centimeter oxide field. But if the oxide is too thin, then you have a direct tunneling, which means the charge will not stay. in the floating gate. So that's not good either. So pretty much the 10 nanometer, this 10 nanometer oxide is fairly standard thickness for non-volatile RAM technology, cell technology. Okay. So in general, we consider the floating gate. Okay, so we have a control gate that tied to the gate voltage, control gate voltage, VCG, and then we have floating gate here. The floating gate is only capacitively coupled. There's no DC connection. It has capacitor to the control gate, or it has a capacitor to the source, drain, and body, shown here. So in general, we can write down the so the total charge on the floating gate is given by the charge of each of the capacitor. Okay, of the four terms. This capacitor from between floating gate and control gate. The second term is between the floating gate and source, and so on. Okay. And then the floating gate voltage. Okay, so we can solve each of them has a VFG in here. Okay, so we can solve the VFG expressed in terms of the charge on the floating gate. Okay, by this way. And so the change in the remember in the beginning we talked about the change of threshold voltage is the delta Q over the C of floating gate between floating gate and control gate. Okay, and so this capacitor, okay, this capacitor cannot be too large, because if it's large, that means you need a lot of charge to shift the threshold voltage. Okay. If it's too small, that's not good either, because then the control gate is not very coupled to the floating. The floating gate is not very coupled to the control gate. Okay. So there's a design compromise of this capacitor between control gate and floating gate, such that you can control the voltage of the floating gate, but without having to put too much charge to shift the threshold voltage. Okay, so that's a program. All right, so we take a 20-minute break. We'll resume at 10:10. Okay, we continue. It's not the right one. Okay, that was the last chart we discussed. This is for the to express uh, the charge on floating gate, the effect of charge on floating gate to change the threshold voltage. Okay, and the next chart is charge erasure by tunneling to the source. Okay, so once you have charge here, how do you get a charge out? And that's by applying a positive charge, positive voltage to the source. Okay, so that the the field between the source and the floating gate is such that the negative charge on the floating gate will tunnel back out to the source. And for that, we need to apply a large source voltage. And in this case, we have to adjust this coupling factor, because if the coupling factor is okay, so we want this coupling factor to be small so that we can have a large erasure field for a given the source voltage. Typically, let's see. Typically, we apply 10 to 12 volts to the erasure voltage here to the source, and it takes very long time. It's about 1 second. Okay? So the erasure time is very long through the follow node line tunneling. So next we talk about the array architecture. There are basically two kinds, NOR and NAND. Okay, this is just terminology. The flash memory array was invented in 1984 by Matsuoka, Japanese, and that's where the term flash comes, because in that case, to erase all the memory cell, you have to use a high field, and so you erase all the cells in a flash. So this shows the operation of a flash array. You can see that each one of those is a flash memory cell. Okay? It's got a control gate and the floating gate. Okay, so the first operation is write. Write means program. So for program, we apply. See, the line we apply a very high voltage, 12 volt. So this is the cell that we want to write. Okay? So we select this cell by applying a high voltage to the gate, and then 6 volt to the drain. Okay, so that we have hard electron injection from this high drain field into the floating gate. Okay, with 6 volt. This is a channel hard electron, so it's faster than photo non tunneling. For read, we pick, let's see, for read, the bit line is only about 1 volt, so we just try to sense whether there's this FET is on or off. The gate is operated 5 volt, so that if there's no charge, okay, remember that if there's no charge, then the VT is high. So 5 volt is not enough to turn on, and there's no current flow between the source and drain. If there's a charge, it's negative charge, then let's see. Let's go back to the. Let's go back to this. If you have charge, the VT is high. So we bias here, it's 5 volt, and there's no current. Okay. And so that's how you read. Okay. And if the FET, if there is current, in other words, the VT is actually lower than 5 volt. Okay. It's lower than 5 volt, then there's no charge. Okay, because the charge makes the VT higher. If there's no charge, then there's a current. If there is charge, then the FET is off because VT is higher. And we will start to read. And for erase, we ground the gate, the word line, and we apply a large positive voltage to the source, 12 volt in this case. Try to get the electron that's stored in the floating gate to tunnel back out to the source. Okay. And that's how we erase. Okay. So this type of architecture we call the NOR architecture, because the cells essentially they are connected in parallel. Okay, and we try to try to measure whether the FET is on or not by say, intermediate gate voltage here. But this kind of cell area is larger because you need contact. You can see that you need so for each cell you need a contact to the bit line. So that's one contact. Also, you have a shared source contact with the other cell. So 1.5 contact. Okay, per cell, and that means that the cell density is not very high. Okay. Instead, we can use the other architecture, which is NAND. So for high density flash array, nowadays we use NAND architecture. But NAND architecture, the cells are connected in series instead of in parallel. So that we don't need any contact for the cell. Okay? They're connected one after another. Okay? But when you connect in series, when you try to see if one of the cell is on or off, the rest of the cell has to be on. Okay. So in other words, the unselected cell, or the word line has to be biased high enough so that whether there's a charge or not, that cell is turned on. Okay. Only the selected cell, let's say word number 3, is in between, so that the whole array, whether it's on or off, depend on whether the selected cell is above VT or below VT. All the rest the gate voltage are above VT, so they are turned on. So if the whole array is on, that means the selected cell is also above VT, which means that VT is lower. And lower means that there's charge injected. There's a negative charge injected. And if the whole array is off, then the selected cell is off, which means that there's no charge, so the VT is high. So with this, we have much better density for the NAND architecture for the cells in series rather than in parallel. Okay. But the speed in NAND is trade-off. The speed of NAND is not as good as NOR because the current, you can see that the current has to go through a lot of other devices, so the read current becomes smaller due to the series resistance of the other unselected cells. So for high density, we use NAND. For high performance, we use NOR. Another problem with this kind of architecture is called over erasure. Over erasure means that when you try to let's go back to the this case. So when you try to erase with high voltage to the source, sometimes there's too much charge tunnel out from the floating gate to the source, so that this floating gate actually becomes there's the net charge on floating gate becomes instead of becomes positive charge. Okay, so that's a problem because then the VT will be too low. Okay? So if one of the devices is over erased, then that device has actually negative VT. If it's negative VT, then it doesn't matter what the word line is, it's always turned on. So in that case, you cannot read it anymore. Okay? So over erasure is a big problem that this fresh array to work properly. Okay. So far we talk about floating gate. It is also possible to store the charge in the gate insulator, and that we talk about MNOS device with a nitride. Okay. Okay. This is floating gate. Okay. This is a floating gate. This is the first simplest floating gate called famous device. Okay. This gate, this is not even a control gate. It's just the floating gate. Okay. And they use the hot electron to, this is actually PFET, so that we have a secondary, so there's hot holes generate the hot secondary electrons into the gate, and that lower the threshold voltage. Okay, so that this becomes without the charge, actually, once you have an electron here, actually it becomes off, because this is PMOS. And for erasure, you cannot tunnel, but you are exposed to UV light to get the charge from the floating gate out. Okay? So the UV has to have the wavelength has to be short enough that energy is exceed 4.2 eV, so that the electron actually comes out of the valence band. From the valence band, that's band gap 1.1 plus 3.1 eV is the barrier height, so 4.2 eV to remove the electron from the folding gate. Okay, this is standard. So the rest of this chapter we just go over different kind of non-volatile NVLM cell arrays that people fabricated. In this case, it's the simplest control gate and stack floating gate, but with the source area intentionally overlap. So we increase the overlap area so that it's easier to erase, because we have a larger area for the tunneling current to erase the charge stored in the floating gate. Another cell, we call it we have two floating gates. One floating gate is under the control gate. Another we call the sidewall floating gate. Okay. The purpose for that is to make the injection occur near the source instead of near the drain. Okay. So you can see that because the coupling of the sidewall to the control gate is weaker, so when you apply the voltage to turn on the device at the control gate, the sidewall, this is only weakly turned on, so the field is highest near the gap between the control gate and the sidewall. And so this becomes the source side injection. A variation of that is to actually connect the sidewall to another gate voltage. It's called a select gate. This one is a floating gate. There's no contact. But if you have a contact, we call this a select gate. So now you have a two device cell. And with two device cell is even more flexible. But of course, the area of the cell will go up for making contact to the select gate. There's also the split and stacked gate shown here. Yeah. And so the floating here, the control gate, instead of right on top of the floating gate, it has this split shape. And so part of the control gate is over direct over the channel. So in this case, when we program the injection near the drain into the floating gate, and when you erase, the charge on the floating gate can tunnel out of the control gate or out of the drain here. Okay. Okay. Again, we talked about this before with PFAT versus NFAT. NFAT, the injection efficiency is poor. With PFAT, injection is better because for PFAT, when the vertical field in the oxide is in favor of injection of negative charge into the gate for PFAT. Okay. So the efficiency is about 10,000 times better. Okay. Another type of E-square problem is with charge stored in the insulator, and SL2 does not have enough charge density in the film to trap the charge for this for the MeRAM application. So we have to use something else. For example, silicon nitride, aluminum oxide, almost anything else can have a much higher trap density than SiO2. Furthermore, we can we can engineer this insulator stack, okay, to improve program and the erasure characteristics. In this case, when the charge is stored in an insulator, then it doesn't have to be uniform over between the source and drain. So in this case, for example, the charge injected is near the right side. Okay, and so now we can have additional flexibility in terms of the number of bits per cell. Okay. So for example, in this case, we can measure the current as a function of gate voltage in two ways, either with a low drain bias or with a high drain bias. Okay. With a low drain bias, okay, we'll consider low drain bias. So schematically, if there's no charge injection, okay, that's the curve. And with the charge injection, the VT becomes higher because of negative charge here, the blue, shown blue by blue. Okay. But if we use a high drain bias, okay, VDS is high. Okay. In that case, we can measure, okay, before injection, that's the same. Okay. After injection, if you measure the same way, the shift actually is very small, and that's because in this case the VT shift is localized. Okay, it's localized near the drain. Now remember that when you apply a high drain bias, the inversion charge near the drain is small to begin with. So in that case, at high drain, the shift, okay, in the red case is small. But if you reverse the source and drain, in the blue case, okay, if you reverse using the right side as the source, the left side as the drain, so in that case, the charge injected is near the source. In that case, you have a large VT shift. Okay. So now we can use this method to detect more than 1 bit per cell. You can have 2 bit per cell. Okay, like in this case. So, so we can. Okay, so in general, so here this is not floating gate. This is silicon nitride, right, with traps, and you can trap on the right side or on the left side. Okay. And so now you have 4 different states. You have 2 bits per cell. And to do that, you make the measurement. You make the high drain measurement. Well, go back to. Okay, we use this measurement. Okay, to distinguish whether the location of the charge is near the source or near the drain. Okay. So for example, there will be four states. Either there's no charge on either side, or there's charge on left, but no charge on right, or there's no charge on left, but there's charge on right, or both left and right have charge. Okay. So we can see that these 4 states can be measured by measuring the current, measure the IV curve with the source and drain reversed. Okay. So you measure the source, the IV twice. With normal means the drain is high. Reverse mode, it means the source is high. Okay. And if in both cases the VT is low, then there's no charge on either side. Okay. But if in one case the VT becomes higher, that means there's a charge. When that side is used as a source. Okay. And if there are charge on both sides, then in both normal and reversed, you have high VT. Okay. So you can altogether you have 4 cases by measuring the VT twice with source drain, with source and drain, left source, right drain, or left drain, right source. Okay. So in each measurement, the VT can be low or high, and there are 2 measurements. So 2 times 2, there are 4, all 4 states. So in this case, in principle, we can have a much higher density because now you have 2 bits per cell if the charge is stored in the gate insulator. Okay. The next one, the next topic is about the tunnel insulator, or the pure SiO2. Okay. When you measure the tunneling current versus gate voltage, okay, it's shown by this curve. And so it stays low until you get to very high field and it starts to break down. Okay. And then all of a sudden it breaks down. Okay. So that's this curve. But you can intentionally put the so-called silicon-rich oxide, SRO. In that case, the current becomes more gradual. instead of jump this very low current, and then when it's a 5 volt or 6 volt, and then suddenly the current jumps. The current starts to leak even when the gate voltage is 2 volts. Okay, so this is more gradual. I call it silicon-rich oxide. And so in this case, we can adjust the silicon content of this oxide for desired characteristics for the IV. Next is endurance. Endurance, okay, so this schematic about the threshold voltage shift between the no charge injection or charge injection. Erase means there's no charge. Red means there's a charge. So initially, this is a time log scale. So initially, there's a big window between erasure and the program. So you can tell the big threshold voltage shift. But as time goes on, we program erase because when you program erase, this is all high field operation. So we have a high field. The insulator actually got damaged. So SiO2 is the degradation due to high field effects. Okay. You produce electron hole traps, and you have defect generation and build up. Okay. So the memory, we call this memory window, becomes smaller and smaller as time goes on. Eventually, you cannot distinguish between the erase state and the program state. In that case, the cell, of course, doesn't work. Okay. So that's called endurance. So after a certain cycle of operation, the E-square problem will not work, and that's because of we usually need a very high field to program and erase, and that will damage the oxide over a long time. Okay, so this is say the oxide degradation. We try to erase by tunneling the electric charge from floating gate back to the source. Okay, so apply very high voltage over here, and that will degrade, cause oxide degradation on the source side. Charge to break down. Okay. So this is again, this is like the wear out of the oxide, and let's see. Okay, so that's a function of charge density, and okay, so when you have a charge, program and erase. Okay, one operation is 6 times 10 to the 12 electrons per centimeter square, and okay, so you can tolerate about 10 to the 7 cycles. Yeah. For 6 nanometer oxide. Also, this is the current through the oxide as a function of gate voltage, Okay, so initially there's no current until you get a very high gate voltage. But once you program erase many times, the oxide starts to be leaky, even at voltage less than 5 volts. So in that case, it will affect the retention time of the stored memory. Okay. So altogether, for so the non-volatile RAM is very different from the static RAM and dynamic RAM we talk about in the beginning of the chapter. For static RAM, dynamic RAM, they operate at low voltage, and then we can read and write as many times as we want. And there's no change. But for non-volatile device, we use a very high field to operate. There's a wear out, so there's endurance, and usually charge to breakdown from that is the 10 to the 7 cycles, and from the leakage current point of view is the 10 to the 5. Okay. So usually we expect between 1,000 and 1 million cycles that we can read and write a fresh memory. Okay. So from this point of view, it's very different from the SRAM and dynamic RAM. And data retention, we mentioned that before. Data retention depend on the leakage current through the oxide. Okay, and this will also, if the fresh E-square prom, it can keep the data for at least 10 years. Some will specify it as keep the data for 25 years. Okay, but as you program erase, the data retention time will decrease, and so there's a certain design spec for the E-square prom as far as data retention time is concerned. Okay. So the minimum may be 10 years with a number of cycles. Okay. All right, so this is pretty much the end of chapter 12. Okay. We still have a few minutes left. Let's see. Let me just stop sharing. Okay. In the third period in today, Sun Yuanzang, Ding Sun will go over some of the emerging memory cells. Okay. Now, let me just say a few words about the last class next Monday. Next Monday, December 9th, is the last class. So what I'll do is to first we'll cover the optoelectronic devices, okay, which is beyond the book. The book is only about the logic and memory in computers. Okay. So we'll cover that in addition to the questions. Okay. And then the time that's left next Monday, I will review for the final exam. Okay, the final exam is December 16th, 2 weeks from today, and that cover all the chapters that we went through. Okay, so that's a lot of material. So I will try to help by reviewing, by spending the second and maybe the third period of the next Monday's class, reviewing the finals of previous final exams. Okay, for example, I'll go over some examples of the finals I gave last year to this class, or so 2023 or even 2022, and so go over that, try to help you prepare for the final exam 2 weeks from today. Okay, I will make an announcement on that. I just want to spend a couple minutes to say that. Okay. All right, so we'll take a we'll end this a little early. I guess Jack will come on before 11:10, okay, and to cover the last part on the emerging memory devices. By the way, the final review for the next week will not be recorded. Okay, so you have to attend either in person or well, pretty much in person. Okay, no recording. All right, so that's see you next week.
Okay, thank you.